All right, so back in the chemistry unit, we talked about physical properties, okay? And we talked about those being like, you know, appearance, odor, solubility, aqueous conductivity, pH, right, color, and all that kind of stuff, okay? Well, the thing we're going to talk about today, specific heat capacity, is also a physical property. That's why we call it specific heat capacity. It is specific to each material. Each material has its own heat capacity. Now, what is heat capacity? Well, heat capacity is how quickly, or rather more accurately, how much energy is required to change the temperature of 1 gram of a specific material. Okay? So let's say I had a gram of water in my hand. So, you know, I'd have a little puddle of water about the size of a raisin in my hand, right? When that water is in my hand, if it's, you know, let's say it came out of the tap, so it's about 5 degrees Celsius, what's it going to do in my hand? Right? If the water's 5 degrees, my hand is 37, what's going to happen to the water? It's going to warm up. It's already, if it was ice, it would melt. You're totally right, yeah. But if it's liquid water, okay, it's just going to warm up, right? Is that going to take some energy away from my hand? Right? Like I would feel the coolness of the water on my hand, okay? But I'm going to transfer heat to it, and the water's going to warm up, okay? It actually takes quite a while, quite a lot of energy to heat water, right? That's where we get the expression, a watched pot never boils. Right? It actually takes a very long time to change the temperature of water because water has an exceptionally high specific heat capacity. That is why living next to a large body of water has an effect on your climate. Remember we said it has a regulating effect on the temperature of that specific area. Here's why. For water, 4.2 joules of energy is required to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, that is a very high specific heat capacity. Right? That's why it takes a long time to heat water up to boiling. And in terms of climate, if I'm next to the ocean, okay, and a cold front, which is cold air, comes into my area, it's not going to affect Vancouver in the same way that cold front would affect Calgary. Because that cold air gets to Vancouver and it's over the ocean, which is not cold. Well, I mean cold, okay? It's not below freezing, right? So naturally, the second law of thermodynamics would say that energy would come out of the water and into the air. Well, air has a way lower heat capacity than water does. And so the temperature, the energy is coming out of the water, it's warming the air, but the water doesn't actually change temperature very much. It can lose a lot of energy, but it won't change temperature very much, okay? Which then, of course, keeps the climate of that area a little more regulated, right? That same cold front of really cold Arctic air comes over Calgary and it just goes to -40. Okay? We don't have anything around here that can absorb that kind of, well, or can give off that kind of energy and regulate our climate. Okay? Does that sort of make sense? Okay? So specific heat capacity has a fair number of applications. The first one is the one we just went over, its effect on climate. Okay? But it also is kind of material chemistry. Would I want to make cookware, pots and pans, out of a material that takes a lot of energy to warm up? No. I want my pan to get hot right away. I want to put it on the stove and be ready to cook. Okay? I wouldn't want to use something with a high specific heat capacity because then it would take forever to heat the pan, okay? And I wouldn't get to cooking. Okay? That's why we make pans typically out of metal. Most metals have a very low specific heat capacity, like cast iron, for example. Okay? By comparison, iron is 0.460 joules per gram degree Celsius. Okay? It's 10 times less. Well, almost 10 times less. Okay, to heat up a gram of iron than to heat up a gram of water, right? Why do we make pans out of cast iron, okay, or copper, other materials? Okay. That sort of making sense? All right, so all you have to know about specific heat capacity is essentially what I just told you, what it is. It's, you know, how much energy is required to heat up a specific material. And you need to know its relationship to factors affecting climate, that is proximity to the ocean. Okay, those two things, and that's really what you need to know about specific heat capacity. All right. Now, the units for specific heat capacity are kind of weird, right? Joules per gram degree Celsius. Okay, they seem weird, but when you analyze them, they're logical. 4.2 joules for every gram to change by 1 degree Celsius, joules per gram degree Celsius. Okay, those are the units for specific heat capacity. Right. Now, I've put 2 specific heat capacities on the board. You actually have a list of specific heat capacities on the first page of your digital workbook for this unit. You will never be required to memorize those. Okay? If I give you a problem on a unit exam or a final exam that involves specific heat capacity, I will give that to you. Okay? You will never have to memorize those numbers. Okay? I just don't want anyone going home and frantically memorizing those. You don't have to. Okay? In fact, if you look at your formula sheet right now, okay, you actually have a few on there as well. You have the specific heat capacity of ice, the specific heat capacity of water, and the specific heat capacity of steam. Okay? All listed on there because we use those ones pretty often. All right. Now, mathematically speaking, we got to do a little bit of mathematical analysis here with heat capacity, right? We can use heat capacity to calculate how much energy would be required to raise, or rather change, the temperature of a given amount of a given substance. Okay? That formula is E equals M times C times delta T. Right? M would stand for mass. Now, this is not physics, this is thermal chemistry. So mass is going to be in grams for this, okay? That's why up here it's joules per gram, not joules per kilogram, okay? So it's joules per gram, okay? So that would be mass in grams. C is the specific heat capacity. So these numbers here of the given material. So you plug in a different number depending on what material it was. And delta T, what does delta always mean? Change. Final minus initial, right? Okay. What does the capital T represent? Temperature in degrees Celsius. Okay. So if I take that formula and I multiply those 3 things together, that will calculate for me the amount of joules necessary to carry out that change in temperature. Right? So if we're just looking at this unit-wise, I would be taking something in grams, multiplying it by something in joules per gram degrees Celsius, and then multiplying that by degrees Celsius. Okay, so when I do that, the grams would cancel, the degrees Celsius would cancel, and I'm left with the right units, joules for energy. Okay? Mathematically, is that formula going to be ridiculously easy to use? Right? Everything's in a line, so everything is being multiplied together. If I want to calculate M, what do I do with C and delta T? Divide them over to the other side. Guys, whatever you want to isolate, you divide everything else over. This formula is like one of the easiest ones you had. After physics, like this is child's play. All right? Everybody with me there? I'm not going to challenge you mathematically with this. All right, so as we said, E is the energy in joules, M is the mass of the substance, delta T is the change in temperature, okay, and that means final minus initial. So there's a little bit of problem solving to do with this formula, like I said, but it's super easy. Okay, so we'll look at that. The practical application part, we already said, okay, to do with some things heat up faster than others, so a little bit of material stuff and its effect on climate, okay. All right, I would like you to write this question down. I'll do what I do with every new formula. We're going to go through all the different derivations or manipulations of that formula. let's have a look at this one. All right, so if we're reading through this question, it's asking for how much heat or how much thermal energy is needed. What am I looking for? Which part of the formula? E. Heat or energy is always represented by E. All right, so we're looking for E. Is needed to raise the temperature of 150 grams of water. All right, so they just gave me mass. And they told me it's water. So because it's water, I also know the specific heat capacity, 4.2 joules per gram degree Celsius, which they gave me actually in brackets afterwards. And I'm heating it from 5 to 85 degrees Celsius. What's my change in temperature? 80 degrees Celsius. All right, so I've got M, I've got C, and I've got delta T. Right? I'm looking for E. So I would get 1 mark for my givens. Okay? E equals MC delta T, okay? And that would be 150 grams times 4.2 joules per gram degree Celsius times 80 degrees Celsius. Right? I just have to multiply those things together. I think it comes up to 50,400 joules. Okay, and the grams cancel, the degrees Celsius cancel, okay, and you're left with joules. All right, so this one would be probably 3 marks. Okay, you don't have to do very much for this. Okay, questions on how that one worked? What if they gave you a material other than water and they didn't write C in here? Then what do you do? Then you go to the first page of your digital workbook where there's a list of materials and their specific heat capacity. So if it just said copper, well then I would go and all right, copper's 0.390. It's one of the lowest. Copper and silver and gold are like some of the lowest specific heat capacities. Gold heats up really quick. Okay? It's why putting on cold jewelry doesn't make you cold. It just warms up really, really fast. Okay? All right. Write that one down, give it a try. Anybody want more time on that one? Okay, let's have a look at it here. So on this one, they're asking me, what's the material? So what am I solving for in the formula? What thing in the formula would be specific to a certain material? Specific heat capacity, yeah. I'm solving for C. That's the only way I can identify the material. What I'm going to have to do is calculate what that number is and then look at my chart and go, oh, it corresponds to this thing, right? So the context here is that it's a 100-gram cup, okay? So we know the mass, okay? And we know that it takes 4,200 joules worth of energy to raise its temperature from 12 to 62 degrees. What's my temperature change? 50 degrees Celsius. All right, so I know I'm going to use this formula, E equals mc delta T, but now I'm looking for C. So I've got to take the other two over to the other side. Now, a little trick here, okay, like all the other formulas we've used, when you do that, you got to make sure that bottom part is in brackets, okay? So you would get a mark for your givens, you'd get a mark for MC delta T, you'd get a mark for your algebra / plugging in of numbers. So 4,200 divided by 100 times 50. Okay, I'm pretty sure that comes up to like 0.84. Yeah, right there, 0.84, okay. That's supposed to be a 0, that doesn't work out well. 0.84 joules per gram degree Celsius, okay, because I'd be dividing by joules times grams times degrees Celsius. Okay, 0.84 when I look at my chart corresponds to glass. Well, that makes sense, it's a cup. Cups can be made of glass. Okay, perfect, I must have done it right then. Okay, everybody all right with that one? Okay, so that would probably be a 4-mark question on the test. Questions on how that one worked? All right, is the manipulation very hard? Okay. Like it doesn't matter what on the other side you're solving for, you divide the other two things to the other side. Okay, this is as tricky as they get. This one wants the final temperature. This would be a 5-mark because it has one little tiny easy extra step at the end. Okay, I'll give you a little bit of time to try that. It's in the digital. Oh, first page. Yeah, it's on Google. Yes, sir. Guys, just in case anyone's wondering where I got that chart, okay, so I went into the class work tab and I went to the worksheet packages and other materials, and it's the global systems worksheet package. Okay, I just opened up that Google Doc and scrolled past the title page. This is the first page. Okay. Anybody want more time on that one? Okay. So like I said, this is the trickiest that they get, and it's not really tricky, it just has an extra step at the end. Okay, so we're looking for the final temperature, okay? Which means we probably don't have this, because it's pretty hard to know what that is if you don't have final and initial, agreed? Okay, so I'm probably going to end up looking for this, okay, as part of the formula, and then go on from there. Now they do tell me the mass. It's 185 grams, and they tell me it's iron. Well, the specific heat capacity of iron is 0.46, okay, joules per gram degree Celsius, and they tell me 200 joules worth of energy is used. That's not very much. 200 joules is not a lot of energy. Okay, so I've got E, I've got C, and I've got M. So I don't have delta T. That's the only thing I don't have. Right, so I'm going to do this, E equals M times C times delta T. Okay, sorry, I do have initial temperature. I forgot to write that down. Okay, I have the initial temperature, it's 7 degrees Celsius. All right, I've got to solve for delta T. What do I do with M and C? If I'm multiplying all these together, I want to move M and C, what do? Divide. Yeah. Okay, if I want to move something, I do the opposite. What I do to one side, I do to the other. Now I'm solving for delta T. So I would get a mark for this. I'd get a mark for E equals MC delta T. I'd get a mark for my algebra. So 200 divided by 185 times 0.46. And so when I do that, I should end up with like 2.35 degrees Celsius. Okay, so when you punch it into your calculator, okay, it's 200, then the bottom is in brackets, 185 times 0.46 gives me 2.35 degrees Celsius. Not very much, right? It's not warming up very much, but it's also not a lot of energy, and it's a fair chunk of iron. It's 185 grams. Okay, so that's not an unreasonable number for the temperature change for this situation. Okay, so you're up to 3 marks here. I want final temperature. I now know delta. Okay, I know it's 2.35 degrees Celsius, and I know the initial. Okay, so delta T, like any other delta, is final minus initial. And you may not have bothered to do this. You probably just did this in your head. Okay, but if I want to know the final, what do I have to do with the initial? Add it over to the other side. So I'll have delta T plus the initial temperature equals the final temperature. I mean, that makes sense. The initial plus however much I changed it by. Okay, so 2.35 plus 7 is 9.35 degrees Celsius. So this would end up being a 5-mark question. Okay, because it's got that extra step at the end where you have to add 2 numbers together. Okay. All right. Questions on that one? That's as hard as they get. Okay, you guys are not going to have any trouble with that. So I would like you guys to try a few from the digital workbook here. I've been recording this whole time. Okay, so what I'm looking for you guys to do here. Oh crap. Okay, so the numbers circled in blue are the ones that we're going to go over. So I need you to write down the numbers so you can look them up because I can't show all of them at the same time on my screen. Okay, so I want you guys to do number 3, number 8, number 14, and number 18. Basically, it's one each of every manipulation of the formula. Okay? So one's going to ask you for E, one's going to ask for M, one's going to ask for delta T, and one's going to ask for C. All right, so 18, 14, 8, and 3 are the ones I want you working on. I'll give you a bit of time on those, and then if any of them give us trouble, we'll go through them together. Okay, the next thing we need to talk about is latent heat. Now, we already talked a little bit about latent heat, but we talked about latent heat within the context of global energy transfers. Okay? It's a big source of energy that's moved around by the water cycle and the jet stream and all of that good stuff that we already talked about. Okay? And yes, that's important. That's its role in global energy transfers. But now we need to look at it from a more mathematical perspective. Okay, in terms of why is this such a big deal? Okay, why is there so much energy involved in moving latent heat from one place to another? Okay, so to start out with that, we first have to kind of look at what is latent heat. Latent heat is the energy involved in a change in state. So going from a solid to a liquid, or going from a liquid to a vapor, or the other way around, condensing from a vapor into a liquid, or freezing from a liquid into a solid, right? Either one of those. But here's the thing. If you had a block of ice, let's say 200 grams of ice, you put it in a pan and you had a temperature probe frozen into it. Okay? When you turn on the stove, what happens to the ice? Or is your knee-jerk reaction, it melts? Okay, that's our knee-jerk reaction. But you know what it does before it melts? What temperature does ice melt at? Oh my God, please tell me you know the answer to this. What temperature does ice melt at?
1.
Actually, one less than that.
0.
0, yeah. The melting and freezing point is the same number, right? It's 0 degrees Celsius. Okay, so first, the ice has to heat up. We don't ever notice that part because it happens pretty quickly. Okay? But in actual fact, the block of ice first has to heat to 0 degrees, then it will start to melt. Okay? Now what you'll see with your temperature probe, okay, if it's recording data while you're heating it up, is you'll first see that the temperature of the ice goes from, let's say we started at minus 25 to 0. And then the temperature probe will stick. And it will stay at 0 until all the ice is gone. Because it takes a lot of energy to melt the ice. Okay? Here's the other weird thing. When we were talking about mechanical energy back in the last unit, okay, you could change the potential energy of an object and the kinetic energy of an object at the same time. You can't do that with thermal energy. Thermal energy, you can change the kinetic thermal energy of a material or the potential energy of the material, but not both at the same time, because they involve a fundamental change in the way the atoms or particles of that material are arranged. Okay? So when you first started adding heat to the block of ice, the particles in the ice were jammed together. Okay? They start to move and they move more quickly, and the hotter it gets, the faster they move, but they're limited by the state they're in. They eventually get to the point where they can't go any faster in that state. They want to move faster, but they can't. So the temperature stops changing, and then the molecules or particles move apart. Okay? That's a change in potential thermal energy because they can go back together again. Okay? It's potential energy in the same way that lifting something off the ground gives it potential mechanical energy. Okay? If I move the particles apart, they have the potential to go back together again. Okay? So while the state is changing, those particles are moving further apart, and I'm changing the potential thermal energy of the material. Well, temperature doesn't measure potential thermal energy. Temperature measures how fast the particles are moving. Okay? By literally, okay, if I've got a temperature probe in that block of ice, it measures how often particles hit it. Okay? That's how it measures the kinetic thermal energy. It cannot measure particles moving apart. Okay? Temperature doesn't measure that. So our temperature probe looks like nothing is happening, but the stove's still on. Okay? Energy is still going in, and the ice melts. Once all the ice is gone, what will happen to the water? It'll heat up. This is why we put ice in our drinks. Right? You put ice in your drink and it stays cold until all the ice is gone and it starts to warm up. Okay? Literally every little bit of ice, it'll stay at around probably 2 degrees Celsius, 3 degrees Celsius, but it'll stay there until all the ice is melted. And then once the ice is melted, you got this diluted drink and it's starting to get warm and it's gross. Okay? So that kind of makes sense? Right? All that, when you put the ice in there, what's happening is the energy from the drink is being used to melt the ice to pull those particles further apart, okay? And it keeps your drink at a uniform temperature until it's all gone, okay? Now, once I get to here and all the ice is melted, then I keep adding energy and the temperature of the water goes up until it gets to what temperature? 100, because that's the temperature water boils at. That's the temperature water goes from liquid to gas. Okay? Now, if you look at the graph there, it also shows that during that phase, the temperature remains the same. Energy is being poured in, but the temperature isn't changing. That's because the liquid molecules are going to a gaseous state. They're moving even further apart. Okay? They're gaining even more total thermal energy because their potential thermal energy is increasing. Okay? How many people have learned this in like a foods class or something? Really be careful of steam. Steam burns you far worse than water. Okay? You guys been told that before? Okay? What if the steam is at 100 degrees and the water is 100 degrees? Does the steam still burn you worse? Absolutely it does. Why? They're at the same temperature. Why is steam so dangerous if they're the same temperature? Okay. The answer is on this graph. Water at 100 degrees has 15 kilojoules of total thermal energy for whatever mass we're dealing with here. Okay? Steam at 100 degrees has 55 kilojoules of energy. It's a lot more because steam's particles are this far apart. Water's molecules are this far apart. Okay? So if steam were to suddenly cool, maybe you reach across a pan, okay, it's got its lid on, and the lid moves because it's boiling and some steam comes out and hits you on your arm, okay? That steam hits your arm and immediately condenses back into liquid water. When it does that, it gives off all of this energy, 40.67 kilojoules worth of energy that liquid water at 100 degrees Celsius doesn't have. Okay? It's actually the potential thermal energy that burns you. Okay? I mean, sure, 100 degrees Celsius burns you too, but okay, it's all that extra energy of change of state. Okay? Is that making some sense? Okay? Here's the other part of it. If you, when you first get out of the shower, do you feel kind of cool, like cold, almost chilled when you first get out? Okay? You've just been in a nice hot shower, you get out, you're reaching for the towel, and ooh, geez, suddenly I feel cold. Why? Why do you suddenly feel chilled when you get out of the shower? Are you covered in water? You have a nice thin film of water on you? What's that water doing? It's evaporating. Okay? All that thin layer of water that's on your body is starting to evaporate. Where's it getting the energy to evaporate from? Your body. It's the same thing that sweat does. Okay? When you sweat, you get a thin layer of perspiration. Or maybe you sweat like some people, and you get a dripping layer of perspiration on your body. Some people sweat differently, right? Okay? So if I get this thin layer of perspiration on my skin, and it starts to evaporate, every gram of water that evaporates, or sweat that evaporates from my body, takes 2,260 joules of energy with it. Cools you off pretty fast. Okay? Sweat works really well. Okay, in order to cool your body. Or maybe you've been to Stampede, right? And they have those like misting stations, right? And you walk through and you've got a nice little bit of mist on you and it evaporates quickly and you feel so much cooler. Same thing. Every gram of water that evaporates from you takes energy to do it. Okay? And it cools you off very quickly. Okay? Similar down here, okay, on this part. Anybody in here made a snowball with their bare hands before? Okay, to make your hands pretty cold pretty fast. All right, so you grab the snow, and it's probably pretty close to zero. Maybe it's like -5. It doesn't take much energy to get it to zero. And now it's melting in your hand. Well, every gram of snow that gets melted by your hands takes 333 joules of energy to do it. Okay? Your hands get cold pretty fast, donating, like, I mean, you're probably gonna melt 3-4 grams worth of snow when you're making a snowball, okay? Maybe more. So you're talking like 1,000 joules of energy, thermal energy from your hands to make one snowball. Right? Your hands get pretty cold pretty fast. And then on top of that, now you got water on your hands. Water's going to start to evaporate. Okay? You're going to lose energy that way as well. Okay? It's all bad making a snowball with your bare hands. It really makes your hands cold. Okay? But there's the explanation as to why. Okay? If you want to put food in a cooler and keep it cold, what do you throw in there? What goes in a cooler, guys? Please tell me you know the answer. Ice. Why don't you just fill it full of cold water? Most of the time people say, like, I don't want a soggy sandwich. But eventually the ice turns to water. Okay? But we throw ice in because ice starts here on the graph. Water starts here. Okay? Water doesn't have the same ability to absorb heat and keep things cool as ice does. Even if the ice was at 0 degrees and the water was at 0 degrees, ice can still absorb more energy. That's why we use it. Okay? Those practical applications make a little sense? Okay, so what you're going to be asked to do is mathematically determine how much energy would be required to take a certain mass of ice, water, whatever, and change it to, let's say you started with ice at -10 and you needed to get it to water at 80 degrees. Okay, calculate how much energy that would require. Right? So what you would do is go, okay, on my graph here, I'm starting at -10, which would be about here, and I'm going to 85, which would be about here. How many steps to this situation? Three. Okay, I've got to heat the ice to 0 degrees because ice won't melt until it gets there. So I've got to add energy to it until it gets to 0 degrees. At 0 degrees, if I keep adding energy, what's the ice going to do? What's the ice going to do, guys, when you add energy to it? Please, God, somebody tell me the answer. Well, it's already at 0. So if I keep adding energy, it's going to melt. Thank you. Okay, that would be the second step. The ice is going to melt. Right? Once I've got liquid water at 0 degrees, if I keep adding heat, it's going to heat up. That's 3 different steps. Okay? Now, just earlier today, we learned a formula that tells us how much energy is required to change the temperature of something. Yes? E equals mc delta T. Could I use that to calculate how much energy is required to heat the ice from -10 to 0? Yeah. Because I know the temperature change, it's 10 degrees. I know the material, it's ice. Specific heat capacity of ice is 2.116 joules per gram degree Celsius. There's another weird thing about ice, or about water. Liquid water, ice, and steam all have different heat capacities. Nothing else does that. It's so weird. Okay. In the second step, I've got to figure out how much energy is required to melt it. Can I use this formula for that? I can't, because what's the temperature change during that? 0, right? It goes from 0 to 0. That's going to tell me that requires no energy. The graph clearly says it does. Right? So at this point, I need a different formula. I need a formula that calculates how much energy is required to melt a specific mass of ice. Okay? That formula, nope, not that, LF, sorry, E equals MLF. Mass times the latent heat of fusion. It's a number I told you earlier today. Okay, LF is 333 joules per gram. That's it, joules per gram. Okay, so when you are melting the snowball, making the snowball in your hands, okay, every gram of snow requires 333 joules of energy from your hands in order to melt. So you just take your mass, and you multiply by how much it takes each gram to melt. So mass times LF. Okay? So new formula. Good news about this formula, you never have to manipulate it. You will only ever be asked to calculate energy with that formula. Okay, once I get the ice melted, now I'm here. Now I gotta get the water to here. What formula would I use for that part? Have I got a temperature change there? So can I use this formula again? Now I plug in a specific heat capacity for water, because it's liquid water now. Okay, and I make delta T, I think we said it was going to 85, go to 85. Okay, so with the heating curve of water, what you're gonna get is this. You're gonna get a question that says you've got this much ice, water, whatever, we'll say ice, okay, and it's at this temperature. How much energy would be required to convert it into water at this temperature, or steam at this temperature? Right? And so you would have to do each step and then add all the numbers together at the end. Okay? There's no algebra involved. You're just plugging numbers in and adding them up at the end. Okay? It's actually pretty straightforward stuff. Okay? Once we do a few, you'll see it and you'll be like, oh man, this is so easy compared to what we did last unit. Okay? All right, so here's what we got to understand about the heating curve of water. It has that shape. 0 and 100 are the key temperatures. Okay, ice melts, water freezes at 0, okay, water boils, steam condenses at 100. Got to know those numbers. Okay, and then we got to understand that the biggest part of this is the evaporation part. Right? If we're looking at the amount of energy here, it's like it's 0.91 kilojoules to heat the ice. It's 6.01 kilojoules to melt the ice. Okay, it's 7.5 to heat the water to 100, and then the rest of it is like almost all evaporating the water. Again, that's that whole latent heat stores and transports a huge amount of energy. Okay, that's the biggest energy part of the water cycle. And when that water vapor condenses back into a liquid, it gives all of that back off again. Okay. All right, so on a problem to do with specific heat capacity, okay, I would say your best bet is write down your numbers and then do this. Draw a rough diagram of that heating curve of water, okay, that's in that picture, right? And then what you do is you go, okay, where am I starting? So I'm starting with ice at -10, so that's here. I'm going to water at 85, that's here. Okay, everywhere the line changes direction is a new step. Heat the ice, melt the ice, heat the water, put in the formulas and go. Okay, that's what I should see, right? Okay, everybody understanding latent heat? We're gonna work on the problems. I mean, we'll do a little thing today, but we're gonna do mostly the problem stuff tomorrow. Okay, as long as you understand now why, or you can see now why latent heat is such a big deal for energy transfers, okay, you can understand how and where the energy goes, okay, in this kind of like the water cycle. It's kind of the energy part of the water cycle. Okay, as long as you've got that, you're pretty good. Okay, our latent heats here, remember our latent heat of fusion, that has to do with melting and freezing. Okay, so to melt ice, you put in 333 joules per gram. When water freezes, it gives off 333 joules per gram. Okay, it goes either way. Okay, and so that's the formula. And then for vaporization, okay, the formula is very similar. It's MLV now. Okay, did we not do that on? We didn't do that on the board. Okay, so for this part of the graph, you're vaporizing the water, so that's mass times LV. Okay, and LV, guys, 2,260 joules. I told you that number earlier when we were talking about how sweat works. Don't pack up, we're not done. Okay, how sweat works, okay, it takes all this energy away from you in order to evaporate the sweat. Okay, so that's a lot of energy. That number is on your formula sheet. You don't have to memorize these formulas or the numbers. They're on the back. They're on the formula sheet that you have. Okay. So let's have you copy this one down. And here's what I want you to do. I want you to draw the heating curve. Okay. So I'm going to put it on here so you've got it. Okay. Write this question down and then draw this curve. And what I want from you before the bell goes is to show where this question starts on the curve, where it ends on the curve, and how many steps you would have to do to get your answer. Okay? We'll talk about that before class ends. Okay? So copy this down, including the curve there, identify the start and end and all the steps. Okay, guys, so if we're looking at this one here, how many steps are there? 5. This is as big as the question can get. Okay, we're starting down here with ice. We're ending up here with steam. Okay, so I've got to heat the ice to melting. That's one step, and that's E equals mc delta T. Okay, then I've got to melt the ice. That's step 2. Melting and freezing deals with MLF. Then I've got to heat the water to 100. That's the third step. E equals mc delta T. Then I've got to evaporate the water. That's step 4. That's E equals MLV. And then I've got to heat the steam. That's E equals mc delta T. The only difference is what C I use between ice, water, and steam. All right? So if you can do that, identify the steps. All you're doing is plugging numbers into a formula after that. Okay? We're going to work on some of those tomorrow. Okay? Good work today, guys.